With the Arista Universal Cloud Network Architecture, network operators are now capable of achieving new levels of automation and orchestration within their networks by integrating across the IT stack. A prime example of this is with Arista and VMware enabling network virtualization, with the entire network provisioning workflow being hands-free and software-defined. Rather than just talking in abstract, let's actually dive into a production example of how the network can be a participating element in the provisioning workflow across your server, storage, cloud, and virtualization platforms. To start with, let's assume a simple four-way network spine has been provisioned. Then each leaf switch is simply racked, plugged into the uplinks, the management port, and of course, power. The leaf switch boots up, connects to the network either in-band or out-of-band, is automatically addressed, imaged, and provisioned with its initial configuration, all via Arista zero-touch provisioning. The leaf switches then connect to the central EOS image to enable VXLAN-based network virtualization. As you can see from the network diagram and the leaf switch configuration, we're routing from each leaf switch back to a four-way spine. We're using BGP as the routing protocol to interconnect the leaf to the spine and automate IP reachability. This enables rapid recovery from link or nodal failures, simplified change control and maintenance mode, and can scale from two-way to over 64-way spine width. The automatically deployed configuration on each switch is going to enable automated discovery of VMware and OpenStack virtual machines, auto-provisioning of VLANs via Arista VM Tracer for vSphere and OpenStack, auto-binding of VLAN to VXLAN in the top-of-rack switch acting as a virtual tunnel endpoint, auto-deployment of the inter-VXLAN routing default gateway based on the configuration of the virtualization controller, inter-VXLAN routing from one VNI to another, intelligent first-hop routing with no tromboning of traffic, elimination of IP multicast for flooding of broadcast, unknown, and multicast traffic, automated learning of each MAC to VXLAN virtual tunnel endpoint binding. The IT administrator can then connect in as many servers as the switch has ports to support. As ESX nodes are added, we can see them appear in the VMware vCenter server, and as OpenStack nodes are added, we can see them through the Horizon UI. Now we will go ahead and bring up several virtual desktops via VMware vCenter. Let's put VM1 into VLAN 100, VM2 into VLAN 250, and VM3 into VLAN 500. As you can see, each VM comes up into its assigned VLAN. And if you look at the output on the leaf switch CLI, you can see each VM being appropriately provisioned. The VLAN is unpruned on the trunk port facing the vSwitch. The VLAN is dynamically created in the VLAN database, and traffic is able to be forwarded. Let's spin up a few VMs within the OpenStack environment as well. And again, the provisioning is automated on the network. Now for the test. Let's pull up the virtual desktops for a VM on one screen and have it download streaming video coming from the OpenStack servers. This demonstrates inter-VNI routing from a VMware environment that is dynamically provisioned to an OpenStack environment that is also automatically provisioned. So let's initiate a vMotion for each VMware VM to move to a new server on a new switch, something impossible in a classically routed network. There we go. Each vMotion is started. The video is still streaming to the clients. The VMs are moving and have now moved across the subnet boundary, yet the remote desktop has maintained its connection and everything has worked seamlessly. So let's verify a few things on the leaf switch to make sure there are no smoke or mirrors in this demonstration. First, let's verify this is a routed network topology. This is easily verified via a simple trace route from one host to another. Indeed, to get from VM1 on VLAN 100 to VM3 on VLAN 500, we traverse leaf 1, spine 2, and leaf 3 on different subnets. This is clearly a routed network. Now let's verify that there is no IP multicast on the leaf or spine. A simple command can verify this as well. And yes, no IP multicast is routed on this network. Now let's watch the network logs as we initiate a vMotion one final time. Let's pull up the terminal on both the current switch and the receiving switch. Start the vMotion and we can see the VM moving, the VLAN being torn down, the receiving switch standing up a VLAN, binding it to a VXLAN VNI, instantiating the default gateway, and learning the ARP entry in the ARP table. This has demonstrated auto-deployment of network switches, auto-provisioning of the network segmentation in both VMware and OpenStack environments, inter-VXLAN routing between nodes in VMware, nodes in OpenStack, and hardware virtual tunnel endpoints facing towards end-user computing and central storage targets, elimination of IP multicast in the network for broadcast, unknown, and multicast traffic handling, stateful vMotion across IP network boundaries without traffic loss and without readdressing real-time workloads. And most importantly, at no point have we had to touch the network equipment to enable this level of automation. As you can see from this very involved demo, Arista EOS is the foundation for network programming, delivering full automation of the network and orchestration by integrating as a participating element with the rest of the IT stack, the servers, storage, the virtualization platform, cloud management systems, load balancers, security systems, and so on. With Arista EOS, network engineers can adopt set-it-and-forget-it policies that automatically update based on the real-time configuration of other parts of the IT infrastructure. With Arista EOS, you can truly deploy a software-defined network today and automate your VM farms and clouds while simplifying IT provisioning.